Hello everyone, my name is Boluwatife Ajayi, and today I'll be presenting a prediction for net hourly electrical energy outputs using various features. Throughout this presentation, I'll be walking you through the steps, models, and tools used in building an accurate prediction model. So let's move to the first slide, or the second slide. So this is the introduction. The objective of the project is to predict net hourly electrical energy outputs using features such as temperature, ambient pressure, relative humidity, exhaust vacuum, and the tools I used were Excel and Google Sheets. To begin, we prepared our data by collecting key columns: temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output. Each of those features was normalized to ensure consistency across the dataset. After normalizing, the dataset was split into two parts: 80% for the training set, which would be used to build the model, and 20% for the test set, which would be used to evaluate the model. The data was randomly sorted using a random number column, which helped ensure a non-biased division between the training and test sets. The first 80% of rows were copied into the training set, while the remaining 20% formed the test set. This randomization helps prevent overfitting and ensures the model can generalize to unseen data. So you can see the screenshots of the test sets and the training sets. So to build the model, we installed the analysis tool pack in Excel. The next step was to run the regression analysis. We input the Y range, which consisted of the net hourly electrical energy output, and the X range, which included the selected features. The regression tool helped us evaluate the relationship between these variables and output a regression model. So the formula we used in Excel for the regression analysis is linest brackets Y range, comma X range, comma true, comma true. This formula calculates the coefficients for our model, giving us insights into how each feature affects the target variable. Now let's look at the results of our analysis. For model 1, which used only temperature as the feature, we had an R-squared value of 0.567 and an RMSE of 5.67. This shows that temperature alone doesn't provide the best fit for our data. We then introduced model 2, which used a polynomial regression with temperature and ambient pressure. This improved the R-squared value to 0.945 and lowered the RMSE to 4.50. Now we tested model 3, which was a ridge regression model using temperature and ambient pressure. The R-squared value here was 0.920 and the RMSE was 4.75. Similarly, model 4 used lasso regression with the same features, giving an R-squared of 0.918 and an RMSE of 4.80. Finally, model 5 was another polynomial regression model, this time adding relative humidity alongside temperature and ambient pressure. The R-squared for this model was 0.930 and the RMSE was 4.65. After comparing all 5 models, model 2, the polynomial regression with degree 2, and the features temperature and ambient pressure had the highest R-squared value of 0.945 and one of the lowest RMSE values of 4.50. This suggests that model 2 performed the best among those evaluated and was selected as the final model. To conclude, we successfully built and evaluated several models, and Model 2 was selected as the best performing model for predicting net hourly electrical energy output. Thank you for your attention.